The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment and Health. Eco-Environment and Health is a journal initiated by prestigious scientists with a strong editorial board, including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design, and broadcasting. The experts will accompany you like an harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Hello. So I think it's almost a time. So I'm Chenggu from Nanjing University. So I'm the executive editor of Eco-Environment&Health. First of all, I would like to give a very brief introduction about our journal. So EEH is an international and multidisciplinary peer-reviewed journal designed for publications on the frontiers of ecology, environment, and health, as well as their related disciplines. EEH focuses on the concept of one health to promote green and sustainable development, dealing with the interaction among ecology, environment, and health, and the underlying mechanisms and the interventions. Our mission is one of the most important is to be one of the most important flagship journals in the field of environmental health. So it's just a very brief introduction. So, and also this is a new journal. So we start this EEH talk. So it's a series of webinar. So today we invite Professor Lohmann. I will just give some introduction about Professor Lohmann. Professor Lohmann is a full professor of Oceanography in the University of Rhode Island. He's a well-known researcher in environmental and marine chemistry, in particular linked to the development and use of passive samplers for organic contaminants. Currently, he is the director of Superfund Research Center at URI. More importantly, he is also an editor of EEH. So next, welcome Professor Lohmann to give the presentation about global monitoring of POPs in the waters of the world. Professor Lohmann, please.
Thank you very much, Dr. Gu. Good evening to Nanjing. and thank you very much for this wonderful introduction. Now let me share my screen. And, oops. You can see this now?
Yes. Yes, no problem.
All right, so then what I thought I'm going to share are some of the results that we have from the program we call AQUA-GAPS / Monet. It's about global monitoring of different organic pollutants in the waters of the world. And while I'm talking today, there are, of course, many co-authors, particularly Derek Muir from Environment and Climate Change Canada, Forbes Smedes and Branislav Rana from Restox, and many, many others. So, as you know, the Stockholm Convention, just in line with the focus on EEH, is to protect the human health and the environment from persistent organic pollutants. And initially, it was just what they called the dirty dozen, dioxins, HCB, DDT, and so on. And then over time, more compounds were added. And of course, one part of the convention is to actually make sure that the agreement is a success and actually leads to a decrease in concentrations. And so there are several monitoring programs in place, and one uses human milk. A big one is known as the GAPS program, where passive samplers are used in air. That's called the Global Atmospheric Passive Sampling Program. That's run by Tom Hanna and his team at Environment and Climate Change Canada. And of course, given that planet Earth is mostly a water-based planet, the question was, is there something that we can actually do in water? Most recently, because of PFOS and PFOA, water has been added, but of course there are more compounds that you could measure in water. Because so far the problem has always been that measuring compounds in water is very difficult, because you, in the past, you would have to take a very large volume of water to measure compounds like PCBs or DDT. So the GAPS program, which obviously inspired what I'm going to talk about, uses these stainless steel double bowls and has sites across the world. Some are urban, some rural, agricultural, and then some are even at the polar ends. And they are operated for 3 months. And then depending on the program, it's either long-term monitoring or specific studies. And so they've been able to establish some means of assessing concentrations of pollutants in air and how they change over seasons and over years. And the design is very simple. The double stainless steel bowls are protecting a thin polyurethane foam disc. And then you need to know something about the uptake capacity of that disc and the exposure time, and you can come up with concentrations. And the typical uptake rate is here 4 to 5 cubic meters a day. Now, what probably got this all going, the POPs protocol, was of course this unusual measurement and discovery that a byproduct, alpha HCH, or hexachlorocyclohexane, was present in water, low concentration at the equator, but really high concentrations close to the Arctic. And of course, very, very few people live in the Arctic. And most of the people living there don't use HCH because there's no real agriculture in the far north. So the fact that a contaminant could be a higher concentration in a more remote location was stunning and concerning at the time. And so the results from this study and others were basically then used by Frank Wanya and Don Mackay to come up with this idea of the global fractionation or distillation of POPs. And the idea is that no matter where the compounds are used, they will be mobile, and the mobility will depend on the properties of the chemical and, of course, on environmental processes. But over time, there would be a change in mixtures from low mobility compounds not moving far to high mobility compounds moving very far to colder places where they basically would get stuck or condense out. Most of the transport was thought to be through the atmosphere because that's fast, but there's also slower ocean transport. And also the realization happened that the movement from the point of use to the final point of retention could be in multiple steps. So that was of course, the global idea behind the grasshopping. So with that in mind, we thought that the time had come that we can actually make use of passive samplers in the water, because there have been by now decades of work of using different sampling designs. And over time, of course, we understand the samplers better. We understand their properties, their deployment conditions, and how to make sure that we derive good data. And we thought we had a possibility to use the same kind of samplers to monitor POPs in very different waters across the world. Now, a quick recap for those that don't use passive samplers on a daily basis. Typically, they're very simple tools, but they have a big benefit over other ways of measuring pollutants, because they directly measure the activity or the form of the pollutant that is possible and that is free to diffuse. And that's a measure of the activity or fugacity, whatever you want to call it, of the compound. It works either in the dissolved phase or the gas phase, just like the GAPS program. And in the water phase, that makes it really advantageous, because you don't have to worry about anymore about the problem of what is bound to particles and what is dissolved. And for those that work in the oceans or in the lakes, we know we always have a problem if we take a water sample by just using a grab sample or a bucket or filter some water. We always have to define what is dissolved through what passes through a filter. But of course, the finer you make the filter, the less passes through, but there's always a fraction that you just cannot catch. That's what we then typically call dissolved organic carbon. But at the same time, we know that dissolved organic carbon and these really small particles or colloids, they do bind pollutants. So the differentiation of what is particle bound and what is not is typically determined by the method. With a passive sampler, we don't have that problem, because only compounds that are free to diffuse get into the sampler. Now, while this all sounds great, of course, we still have some work to do. Either we operate the sampler in the linear uptake range, in which case we need to know the sampling rate, or we need to let it equilibrate, and then we need to know the partitioning values at that temperature, potential salinity. Luckily, we can use performance reference compounds that diffuse out of the sampler to establish whether we've reached equilibrium or we're in a linear uptake or somewhere in between. So we can use the loss of the performance reference compounds to correct and thus derive the exact state of equilibrium, and then use the partitioning constant to derive the concentrations. So with that in mind, we met, the team of AQUA-GAPS met, I think it's 5 years ago at Jinan University in China. Eddie Zheng hosted us, and we discussed how we could make an AQUA-GAPS possible. Suspended from a theoretical idea, we could really use passive samplers to how can we actually do this. And so we discussed a few options and then came up with a couple of designs of how we can deploy and protect the samplers. And basically, there's two very different designs. I think by now we would favor the more open design at the right. The open design has the advantage that it enables faster flow of water, so the samplers get more pollutants, so that's easier. The design on the left, which is a more protective design, certainly helps if you have a rougher deployment scenario. Maybe you have bigger waves, or you have to worry about ice conditions, so you want something that is stronger. But of course, because there's fewer holes, the water exchange is slower, so it takes longer times to equilibrate. And basically, those were centrally made and then shipped out to different participants. And on the maps here, you can see there's a range of sites, freshwater in blue and coastal and saltwater sites in pink. That was our initial idea. And then the other part was that we had, luckily, Resetox in the Czech Republic stepped up and say they could run the analysis for all the samples. So what we ended up doing is that Resetox prepared all the passive samplers, all the QA. Those were shipped out to the different participants for deployments. And that deployments were led by either Ontario Ministry of the Environment or URI for freshwater and Resetox, and then Jinan University Resetox for coastal waters. Once the deployments were done, the samples were shipped back to Restox and they were analyzed centrally. So we had uniform quality control, and that was very important to actually make sure that the results were comparable. In terms of contaminants, the initial scope was on some of the legacy compounds, PCBs, organochlorine pesticides, and I'll talk about those today. But we also have PAHs, and then a range of flame retardants, PBDEs, and novel flame retardants, including organophosphate esters. By no means does this mean that is all. In the future, other compounds can be added if there's particular interest. I believe we still have the extracts, so things can be discussed. It's, we're meant to provide a service to the community also. We started off by looking at two different passive sampling types, polyethylenes, PEs, which I have typically worked with, and then silicone rubbers that Restox had a lot of experience with. The deployment started in 2016, but we quickly realized that deploying with global participants is a little more challenging than we anticipated, be that custom problems or shipping problems, deployment problems, losing samplers. So it took a little longer than we'd expected, but we're glad to say that now we have results from numerous sites. Those who have worked with me will understand that this is very painful for me to present this slide. It shows the detection frequency of a range of compounds, as in this case, it's all the PCBs, DDTs, and other organochlorine compounds in silicone on the left-hand side in the olive green, and then in the polyethylene in the darker green. And unfortunately, there is not a single compound where polyethylene had a higher detection frequency. I'll put it the other way around. Silicone was basically as good or better at detecting compounds than polyethylene. So for the rest of the talk, I'll focus on the silicone results because we just get a better coverage. It is, I think, in a simple way, polyethylene is fine for legacy hydrophobic compounds, but as soon as you look at compounds that are more polar, silicone just becomes much better. So a couple of pictures. This is from the Middle East, Sea of Galilee. You see the more protective design. You see a deployment from Colombia, South America, where the pest sampler is deployed down here in a freshwater reservoir. See deployment from South Africa, something from Chile. There you can actually see some polyethylene, and that looks like silicone. And here's the Australian deployment sites. Of course, Australia is not known for having a lot of water, but they had a little bit at least. So you can see the different designs at this point. And so with that, we spent the last 2 years analyzing the data, making sure that the results were reliable, and we finally started looking at what these results actually show us. So here are some snapshots to give you some idea of the spatial distribution. On the left-hand side is Hexagonal Benzene, anything from Antarctic to the Northern Arctic, sites China, Australia, South Africa, Europe, North America, of course. You see a pretty uniform distribution. And we have here alpha hexachlorocyclohexane. We see not very much in most sites. You just see about a small dot. But then we see high concentration in the Canadian Arctic. So some of these pictures already give you some idea of where the conclusions will end up. Maybe some of the polycyclic aromatic hydrocarbons, of course, produced by combustion processes. And not a big surprise, they're of course higher where you have more industrial activity. So clearly some of the European, North American, China and South America are bigger players. This was for pyrene. This is chrysene, also another polycyclic aromatic hydrocarbon. This particular case seems to be a lot in the European region, and that might be because diesel engines were remain very popular in Europe, and PAHs are known to be emitted by diesel engines quite well. So that's kind of the idea of where we have PAHs. And then if you look maybe at flame retardants, here's the legacy compounds, polybrominates diphenyl ether 99. Those PBDEs were heavily used in North America for political reasons, because the flame retardant addition was demanded in products for a long time. And that led to a lot higher PBDE concentration in the North American population, particularly the US and Canada, than, let's say, in Europe, and the way it looks basically anywhere else in the world. And again, that wouldn't be a big surprise, knowing that the US market demanded flame retardants be added. And then here is a replacement compound, triphenyl phosphate, organophosphate ester. This looks like much more widespread and much more similar in concentration for most of the Northern Hemisphere, a little bit in South America, basically. And I'll talk about the Antarctic site a little bit later. But I just want to give you some idea of where we stand with respect to analysis. I should point out that we don't have all results in. We have all results for the PCBs and organochlorine pesticides, over which I talked today, but we don't have all the other results. The final batches are still being analyzed. So today I'll focus on the legacy chlorinated pollutants. And some of the questions we had, knowing what has been published, is for the polychlorinated biphenyls, how far have they actually moved away from where they were used? Because we know global distillation and fractionation would assume that they move in hops away, and you would find higher concentration as you move towards the north. The other part, I'd shown you the graph that showed the trend of hexachlorocyclohexane concentrations in water. That was a combination of different studies. So here we have the same sampling approach in all these waters. So do we get the similar trend? And then do we see any other compounds that could have followed this distillation with high concentration in the north than in the warmer latitudes? And then lastly, we had a few compounds in here, including DDT and endosulfan, that either are still or have been used fairly recently. So do we see that these ongoing applications are still important, or do we see the legacy use dominating? So those were kind of the questions we had in mind. And with that, let's go over to the PCBs. Now, this is, of course, one of the really old chemicals of concern. They were very simple production, where basically you had a biphenyl and then chlorine was added by weight. And you got a number of different congeners, depending on which carbon had a chlorine on it. So we had up to 209 possible congeners. We had a range of properties depending on how many chlorines are added and where they are added. So from very volatile, low-weight PCBs to fairly to compounds with many chlorines that are not as prone to transport. Now, as I started off saying, this is a very old problem. They were used up to the 1970s. Were used a lot in transformers, but also found in paint and so on. Of course, one of the questions one could ask is, why would I still have to worry about PCBs given that they've been banned for 50 years? And there's two things about PCBs that are very interesting. And one is the discovery of PCBs was a complete accident. The chemist Søren Jensen was looking for DDT in the blood of eagles. And then you had what is basically a very early form of an electron capture detector, and you found some other strange wiggles or peaks on his chromatogram. And then upon some further discovery and thinking, he realized that what he had found was actually the presence of PCBs in wildlife. And then he basically ended up saying that PCBs constitute perhaps the most stable group of organic compounds in existence. It poses therefore a threat to life forms. Because by now we know that perfluorinated compounds are even more stable, but of course he was right. PCBs did pose a threat to life forms just as PFAS. That, of course, is a very common theme to recalcitrant chemicals. All right, so why should we still worry about PCBs? Of course, one reason is the enrichment of the food chain. And a very sad example of a few years ago shows that a killer whale named Lulu was beached, as in found dead, on the beach of Scotland. And when she was analyzed, she had roughly 1,000 milligrams of PCBs per kilogram in her blubber, and that was 100 times above a safe threshold. And it's also known that Lulu could never reproduce. And by now there's credible science that suggests that many of the killer whale populations certainly in the North Atlantic, will probably die out because they will not be able to reproduce sufficiently to keep being stable as a population. So even though the corals have been banned, because of the high bioaccumulation, they are found at high concentration in top predators. And of course, these top predators, in theory, pass it on to their young ones. And so the cycle continues. All right, so with that said, onto the data. Where were PCBs actually used? Data from Knut Breivik, basically between roughly 30 and 55 degrees north, where most of the usage. And there was an earlier study that actually looked at PCBs in soils to see how far have PCBs moved. And all the black dots here, as data from Sandra Meyer, shows where PCBs have been found in soils. And you see by and large, the highest points are roughly around 30 to 50 degrees, 55 degrees north. But you see some indication of compounds moving further north and a few outliers in the southern hemisphere. So with that, the soil data would suggest some movement of PCBs to the north, but the majority probably has stayed close to where they were produced. If we now look at our water data, always from the South Pole to the North Pole, and the majority of PCBs you can see is somewhere between 30 and 60. And there's another peak at 35, similar to what we see in the soil. The Antarctic, we had several discussions within the team. We think for various reasons, and I can discuss those later, we think those numbers are probably not reliable. So as we move towards submission of a manuscript, we probably have to exclude it and can give some indication to why that is. But basically, this PCB concentration, you see dominant congener is 153, basically around 40 degrees. If we look back now to where PCBs were used, we see the water data almost perfectly matches production data and usage, and a hint of PCBs moving outside of the usage region. So very similar picture to the soils, even though, of course, water is much more mobile than soils, but overall, PCBs have more or less stayed where they were used. And I should thank Knut Breivik for sharing the usage data with me so I can actually use this plot. All right, so what about DDT? DDT was widely used as a perfect weapon against malaria, typhus, but it was banned in the 70s in a lot of countries. And of course, we know that the problem with DDT is a breakdown product, DDE, that was responsible for the thinning of eggshells, which led to the collapse of a lot of predatory birds in the Northern Hemisphere. There are, of course, some regions where DDT is still used because it remains a very powerful weapon against malaria, which causes a major threat. So here's the data for the DDT, and you can see both concentration of DDT itself in this greenish here, and then the breakdowns DDD and DDE in blue and red. By and large, a lot of DDT in the Northern Hemisphere, very little in the South, and very little indication that it has moved beyond 60 degrees north. If we look at where we see maybe some indication of fresh DDT being used, so we use the ratio of DDT over DDE, and you see some of it is around 30 to 40 degrees north, a little bit in the south, but some indication of fresh, but not too much. And then the third compound that is in this group of more recently still used is endosulfan. It was phased out in the 2000s in many places. It was added to the Stockholm Convention a little later. And the major product we found is endosome sulfate, so already the breakdown product in blue, and that's on the right-hand scale. And you see it's confined to a very narrow band, only Northern Hemisphere, 20 to maybe 70 degrees north. And it's mostly higher concentration are actually in the temperate regions. So no indication of it moving north either. So with that, I think that's kind of the most famous classical legacy compounds. So the PCBs in the water seem not to have moved very far away from where they were used, with a touch or a hint of movement to northern latitudes, but the majority has not. DDTs and endosulfane, we mostly see breakdown products, even though a little bit of recently fresh applied DDT maybe. So with that, I want to switch over to some of the smaller compounds, particularly hexachlorobenzene or pentachlorobenzene. Hexachlorobenzene was used as a fungicide. Again, it was of course also banned in the 70s. It had a pretty large global production volume of over 100,000 tons. We think at least 10 to 26,000 tons has escaped and is in the environment. And our own work suggests the Atlantic Ocean is probably the biggest reservoir on the water side. So what do we see? Again, we see a hexachlorobenzene, that's the higher concentration in this olive green. Pentachlorobenzene, lower concentration in a darker green. High concentration in the northern hemisphere, particularly you can actually see high concentration also at 70, 80 degrees north. Little in the southern hemisphere, and again, the Antarctic data we think we'll have to exclude. So with that in mind, of course, the question is, can we explain this data a little better than just saying there's more in the north? So what we looked for is whether we can find correlation with temperature. And so shown here are plots of the natural log of the dissolved concentration as a function of 1 over temperature. So warmer temperatures are here, colder temperatures are further to the right. So this is where the polar sites end up. This is where the temperate sites are. And if you plot these, you can derive the slope and turn them into the enthalpy of exchange. And in this particular case, what we derived for hexachlorobenzene was 68 kilojoules per mole as the enthalpy of change. The literature from Shannon 1 year is a comparison, and they suggested the air-water exchange is 51 kilojoules per mole. And we did the same for pentachlorobenzene. That's the slightly lower line here. We derived enthalpy of change of around 50 kilojoules per mole. And Shannon 1 year suggests it was 44. So in both cases, the environmental data is close to what the physical chemical properties would suggest based on laboratory measurements. Maybe last word on why did we choose air-water exchange? Because we measured in the surface water and we assumed that the presence of the compounds was driven by atmospheric exchange. So we assumed basically equilibrium with the atmosphere, and assume what we see is now an air-water exchange on one end. The resulting data suggests that our theory is probably valid. So that's why we call them the equilibrium compounds, because if you display air-water exchange enthalpies that are close to prediction, then that would suggest indeed the compound is getting close to equilibrium. For the HCHs, of course, this is a sad story where the technical mixture that was used initially, the active part was only 10 to 50% lindane, gamma HCH, whereas the rest was just waste. But of course, nowadays, alpha HCH is what is most abundant in the environment. And you've seen the data before. There's a very strong tendency to have higher concentration in the Canadian Arctic, a little less so in the temperate northern latitudes, and basically nothing in the south. So a very strong indication of fractionation and cold condensation, just as predicted. And then, I want to be mindful of time. Another few legacy compounds, dieldrin, endrin, aldrin, all banned in the 70s. And we see dieldrin shown here. Again, high concentration Canadian Arctic, less so in the temperate northern and nothing further south. If we look at endrin or aldrin at much lower concentrations, again, endrin, highest concentration in the Canadian Arctic, less so in the temperate and nothing further south. So there's another group of compounds, and we also start to see the evidence of this cold condensation, where concentration are much greater in the cold Canadian Arctic than further south. And then if we look for chlordanes or heptachlor, these are shown here, dominated by cis-chlordane or alpha, high concentration Canadian Arctic, less so in the temperate, and basically nothing in the south. And we see a very similar story for the epoxides, for the breakdown products, trends higher in the Canadian, less so, and very little in the southern hemisphere. So we think that overall we have a decent set of indications that we see some chemicals that are indeed becoming enriched in the northern hemisphere, in the far north where it's colder, and less so as it gets warmer. And so I wanted to convey that first, we think we have finally been able to show that a passive sampler-based global monitoring program can be done. We were successful on most sites, but not at all, because there's always a challenge of deploying something in the water and getting it back. The results that we have so far suggest that PCBs, DDTs, endosulfan, and all of those have not really moved far away from their use region. And of course, by now, in hindsight, we know for PCBs, we see similar results in soils. So the water kind of reinforces prior work, even though we had expected that water as a mobile medium might help move compounds away from their use. Hexachlorobenzene, pentachlorobenzene are very close to equilibrium. And then we have a large group of other legacy chemicals. All of them show that they are mobile, and we see greater concentrations in the Canadian Arctic and the Arctic sites where it's cold, and lower concentration where it gets warmer. And as I said, there's more data to come. We have data on pHs in a range of flame retardants. We also still have a few more data to come for some of the, I think, the chlordanes. So there's some more to come, and some of the calculation might change a little bit, but at the end of the day, this is probably the 95% version. So it's work in progress, but I was glad that I could at least share those. I should thank a lot of people, because in every site, there's always 1, 2, or 3 people who helped figure out where to deploy, how to get it back. Rest docs who spent a lot of time on the analytical work. Paul Helm from Ontario Ministry of the Environment, who did a lot of help to get the passive samples to different freshwater sites. Eddie Zhang and his team from Jinan University to help with the coastal deployments, and of course, you for listening. And I'd be happy to take any questions.
Thank you very much, Professor Lohmann. So any questions? From audience, if you have like, if you just raise your hand, if you have any question.
Hi, Professor Lohmann. Can I have a question?
Of course.
Thank you for your excellent presentation. It's very interesting. As you know, you have many results of the distribution and the concentration of different purpose in global scale. So I'm wondering if you do any source identification of these POPs, especially those main congeners.
Very good question. Two answers. One is, yes, we will do more. It's going to be easier with the polycyclic aromatic hydrocarbons, because there we have the largest suite. We realized for various reasons that on the side of the PCBs, for example, we have only the 7 main congeners, so that makes source identification not as strong as we wish. But to some degree, it's a compromise between getting good results and getting all of the results. This is we have results for over 40 sites, and I think it's 60 or 70 samplers, and then there's QA, QC, so there's a lot of data processed. So unfortunately, we don't have as many PCBs as we would like to do the source identification that you correctly alluded to.
Thank you.
Yeah, thank you. Maybe I can ask one question. When I look at the map, right, in China, only the place with probably from Edison, right? So that's the only site you sample, right? Because if you sample from north, we found some different patterns.
Yes, you are fully right. It's very difficult to capture a place like China well, or any continent well. So it's, I think what we realized after this first round, and the first 2 years are basically one round now, is that we'll have to be a little more strategic how we can find other places. The challenge remains, of course, ideally you want a remote water body that you have easy access to, and both you don't typically have. Either you have a remote or you have easy access. But yes, no, we realize when we look at the map now, we will reach out to make sure we get a better distribution of sites across big countries, continents. Fully agree.
It's already lots of work. Yeah, I understand. Thank you very much. So, Professor Lohmann, some people ask that, do you plan to focus on new organic pollutants in the future? Which one is the best option? Yeah.
Yes, good question. So the simple answer is yes. We'll focus on newer ones, and it depends now if they can be analyzed, or if are taken up by silicone rubber, then yes, we can do that. The group by Jochen Müller, they will add a sampler for PFAS to the network in the next round, so we get PFAS, and of course that sampler will also capture more polar compounds in general. So be that pharmaceuticals or whatever you might be interested in, or modern pesticides. So that is coming. But yeah, I think in the end, the way we wanted to design AQUA-GAPS is that if somebody has a really good idea or a really strong method and thinks they really need global data, that depending on if it's a matter of reanalyzing the extracts we have, that's very easy. If it requires extra samplers, they can probably be added. So it's a matter of reaching out to one of us and say, I would like to do this, and then we can figure out whether we can do this.
Okay, it seems like 2 more questions.
Hi, Lohmann.
Professor Chen, yeah, Professor Chen, yeah.
Hi, Rena.
Hey.
Hi, Rena, can you hear me?
Yes.
Hi, long time no see. I'm Changa Chen. I'm now in Guangzhou.
Good. Nice to see you again.
Sorry, I don't know how to open the video, but I have a question about you just mentioned that the polar chemicals in the future. Maybe in the future we can join, because probably I'm doing the passive sampling with DGT for polar organic chemicals as one thing. We really would like to join in the future if it is possible. Of course,
the simple answer is yes.
Yeah, and also we are developing other sampler, like with the ceramic dosimeter, similar to the ceramic dosimeter, and kind of doing we're targeted doing for the non-targeted. So, and my another question is, have you tried to do a kind of non-target analysis for your samples, because it's very valuable samples, and I'm thinking maybe it's good to see what else in the samplers all over the world.
Yes, valid questions, good questions. When we discussed how to do this, we said yes, we want to make sure that down the road somebody can rerun it and look for other compounds. So far, we just haven't had the time to do any of this. But yes, that is certainly, we'd hope that somebody will do it. Either it's one of us or somebody from the outside. And for adding other samples, the only challenge is that the deployment times now have been typically months. So depending on what sampler you have, if you have to, it would have to be a discussion with basically everybody at a given site whether they can do it within the time that you need. And if you think the DGT will only last, I'm just making this up, 3 weeks for linear uptake, then this might be challenging.
No,
but it's not saying it's impossible. It's just depending on where you are, it's not always clear that people can get back in the time that you need.
Right. Okay. Thank you.
You're welcome.
Thank you. So Professor Li Fei Zhang, right?
Yeah.
Please.
Hello, Rainer. Thank you for your presentation. I have 2 questions. The first one, I noticed that your plan is a big scale globally. I know the ocean flow. Do you consider this? This maybe influence the sampling size, the result. The second question is about HCB and the penta CB. Is there any possible, as I know the HCB in the atmosphere was very high compared to other OCPs. Is there some relations between the air and your results in water? Thank you.
Yeah, thank you for the good question. So we have not yet compared HCB in the air to the water, and which is what we would like to do eventually. Very good point. We just haven't had the time yet. The other question on the ocean, it's funny because when we started the work, we thought AQUA-GAPS would include ocean monitoring, but if you look carefully at the sites we don't have real ocean sites. And it's just the getting access to ocean monitoring is a little more challenging because you really have to rely on existing oceanographic monitoring programs. And those exist, but it's just, we have not made an effort to reach out to get hold of those sites. I think now that we know that the results are promising from the easier land access sites, we'll try to include ocean sites. And I work at ocean sites, but to line up the deployment times hasn't been easy. But yes, good points.
Okay, thank you.
Yeah, another question from the audience is that, so most of the pollutants in the environment are left behind, but lots of aromatic hydrocarbons are local emissions. How to judge the migration of different areas? Migrations of different areas.
Yes. So we had hoped that most of the sites we use are not directly impacted by local emissions. Having said that, it's actually not that easy to accomplish because water does flow and it's not that easy to avoid that. So we have looked for the data we have whether we can make a correlation with population, which would be an indication that we have local emissions. And we see a little bit for PCBs, and we basically see no other significant correlation with population density right now. pHs, I agree, are probably going to be different. We assume at least. We haven't started the analysis interpretation of the pH results yet. And yes, you might be right. We might just see local emissions. Well, maybe let's call that regional emissions.
Right. So any questions from the audience? Because some people from the another, maybe they cannot ask questions. So. Yeah. Okay. It sounds like yeah, we have yeah, Professor Lohmann. Yeah, yes, did a very good job. actually. And I think every people are very satisfied what you just mentioned, or is your presentation, lots of data. And also, as you said, like the new, like emerging contaminant will be in the next list for to do the monitoring, right? Global monitoring. So let's say we also hope, you know, maybe in the future you can give another talk about that part. Thank you very much.
Right. There was a reason why we started with the old chemicals, because we thought if we can show that the results for the old chemicals make sense, then it's easier to justify and explain the trends for new chemicals where we have less information of what the global distribution should be. Yeah. So that's why we started with the easy old ones.
Mm-hmm. Okay. Thank you very much. So yeah.
Thank you.
Mm-hmm. Thank you. Thank you for your support for the EEH. So actually, this
good night.
Yeah. Good night.
Good night.
Mm-hmm. Yeah. Maybe we can just like a little bit more information for every people, because this is our first webinar from the EEH talk. So we plan to have this talk every week. We'll try to invite 2 speakers worldwide to introduce the latest research in the field of environmental health. Actually, like 3 days later, on May 12th, we have the second talk. It's from Professor Huichun Zhang. She is a professor from Case Western University. She will talk about the machine learning. So it's also a very hot topic. So please, you know, like the audience, please check our website or our social media for more updated information. Okay, thank you for your attention. So if you're interested, you can like join our WeChat and Twitter account, and for more information. Mian, can you also show the website? Can you show the website for the EEH?
In the next page of the PPT.
Yeah, just a very quick. Maybe people are very interested. Otherwise, it's okay. So maybe we can do next time. Thank you very much, Lohmann, Professor Lohmann. Thank you.
Thank you, and a good night to everybody.
Yes.
Good night,
yeah.
Thank you.
Bye-bye.
Thank you.
So thank you very much for your attention. So this is our website. If you look at that, so this is lots of information about these journals. Yeah. Okay. All right. All right, B. Okay, so see you next 3 days later on Thursday. So we'll have our second talk. Okay, bye-bye. Have a good night.